This leads us into the true properties of a true solution, where you have a true solute and solvent. And the properties of solutions that are only available to you if you have a solution are called colligative properties. So colligative properties are literally properties only exhibited in a solution. If you have pure solvent like water or pure solute, nickel 2 chloride, whatever, you're not going to see any of these. But if you have a solution, oh wow, now you've got some weird things. There are 4 colligative properties. The first one is you end up having a decreased vapor pressure. So vapor pressure goes down. Sometimes it's called vapor pressure depression. Your melting point goes down as well. So melting points will go down, but boiling points will go up. Boiling points actually increase. And finally, the 4th colligative property, osmosis. Osmosis is a type of a force that happens with solutions, and we'll talk about that in a little bit. Osmosis is the same as osmotic pressure. So if you've heard either one of those terms, we're going to be looking at them both in this section. Colligative properties are something that, again, exists only in solutions. And in a solution, to figure out the strength of these colligative properties, we need to know the number of solute particles relative to the solvent particles. And this is really wild. We don't need to know what kind of solute particles we have. We just need to know the number of solute particles relative to solvent particles. And unfortunately, the concentration unit we've used so much in Chem 221, and we'll continue to use, by the way, molarity, doesn't really do a good job. All right, molarity is about moles of solute per liter of solution. And what we want to have is we want to know somehow the relative number of solute particles relative to solvent particles. So molarity isn't going to cut it. We're going to talk about some new concentration units here in a little bit, and we will talk about how you can relate them back to molarity, because molarity definitely dominates the chemistry world. 3 new concentration units will be very helpful to us in the upcoming sections. And the first one of these new concentration units is called a mole fraction. So let's say you have a mixture of A, B, and C together, and you wish to describe the mole fraction. Well, the mole fraction of A, let's assume we're looking at A, is going to equal the moles of A divided by the total moles. So you're going to have so many moles of A, B, and C. Mole fraction of A would be moles of A on top divided by total moles. And you could have a mole fraction of B. You'd have moles of B divided by total moles. Mole fraction of C would be moles of C divided by total moles on the bottom, and moles of what you're looking at on the top. The other new concentration unit we're going to look at is called molality. And molality sounds a lot like molarity, but molarity has an R and molality doesn't have an R, it's just L's. Molality gets the symbol little m, and please, from here on in, you must use little m for molality, and you must use big M, capital M, for molarity. Molality is defined as the moles of solute over the kilograms of solvent. And that's kind of interesting. Moles of solute over kilograms of solvent. Molarity is moles of solute over liters of solution. So 2 differences between molality and molarity. The top part of both of them is actually the same, but in the denominator, the bottom, molality has the kilograms of solvent, the mass, if you will, of a solvent. Molarity has liters of solution, the volume of solution instead of the mass of the solvent. The third concentration unit is called a weight percent, and weight percent is grams of what you're looking at divided by total grams times 100%. Weight percent is usually a percentage, all right? Mole fraction occasionally is a mole fraction percent, but that's rare, so most of the time it's not. Weight percent, you actually will multiply by 100%. And we're going to talk about how to calculate all 3 of these concentration units from particular data. Let's say that we're going to dissolve 1 mole, which is 60 grams of urea. Urea is a solute, and we're dissolving it in 15 moles, which is 270 grams of water. And the question is, what is the mole fraction of urea? Okay, so this is the kind of problem you might see. And the mole fraction of urea would be moles of urea on top divided by total moles. So urea, we have 1 mole of it. We're going to divide it by total moles. So that would be 1 mole of urea plus 15 moles of water. So mathematically, it would be like 1 divided by 16, and that answer comes out to be 0.063. Mole fractions are always numbers no bigger than 1. If it's equal to 1, then you have just that compound, but more often than not, you'd have a number less than 1 but greater than 0. So the mole fraction of urea, 0.063. And again, we got that from moles of urea divided by total moles. Bam. So let's do an example which goes through more details like the one we just saw. All right, and this is an example we're going to go through a lot here. We're going to dissolve 62.1 grams, which is 1.00 moles of ethylene glycol in 250 grams of water. We can use this information to calculate mole fraction, molality, and weight percent of the ethylene glycol. Ethylene glycol is a diol. The picture of it is right there. There are 2 carbons. There's an OH off each carbon, and the other places are just saturated with hydrogens. But that's not really important right now. We're going to use this information to calculate mole fraction, molality, and weight percent. And when you're doing a problem like this, you need to have grams and moles of solute and solvent. So you can see right away you have grams of solute, that's the ethylene glycol, 62.1. You have moles of solute, 1.00 grams. The molar mass of ethylene glycol is 62.1 grams per mole. You also have 250 grams of water, that's the grams of the solvent. We will need the moles of solvent, moles of water too. So one of the things we're going to have to do is turn 250 grams of water into moles. Let's see how this all works out. First thing we're going to do, turn the grams of solvent into moles of solvent. 250 grams of water divided by 18.02 grams per mole, the molar mass of water. We're going to get the moles of water, which is about 13.9 moles. 3 sig figs in, 3 sig figs out, all that kind of stuff. Now we should have all the pieces we need to find mole fraction, which, by the way, mole fraction gets that little chi, that little X symbol right there. Molality, which is the little m, as well as weight percent or mass percent of the ethylene glycol. So mole fraction of ethylene glycol will be moles of ethylene glycol divided by total moles. And total moles here comes from ethylene glycol and water. So mathematically, you would have 1 on the top divide by 1 plus 13.9. Make sure you put those moles in parentheses. Do not put in your calculator 1 divided by 1 plus 13.9. It'll come out to be 14.9, and that's not the right answer. You want to make sure that the whole denominator is placed in parentheses, or just have 13.9 plus 1, something like that. But make sure you do your math right. In the denominator, make sure that's all in parentheses. Anyway, if you've done it right, mole fraction of ethylene glycol, 0.0672. Woohoo, I know, exciting. Anyway, you can calculate the mole fraction of the second component pretty easy. If you only have 2 components, then the mole fractions of both of them together equal 1. So if you needed to find the mole fraction of the water, you could go 1 minus the mole fraction of ethylene glycol, 0.9328 would be the mole fraction of water. And it didn't really ask for it, but that will be pretty helpful in stuff coming up. Molality is moles of solute over kilograms of solvent. Now, we had 250 grams of water, and there are 1,000 grams in a kilogram. So 250 divided by 1,000 is 0.250 kilograms. So molality, 1.00 divided by 0.250, molality 4.00 molal. That's the molality of the ethylene glycol solution, moles over kilograms. And then finally, the last one we haven't done is the mass percent. That's just equal to grams of the ethylene glycol divided by total grams. So in this problem, 62.1 is the mass of the ethylene glycol. We'll divide it by 62.1 plus 250, ethylene glycol plus the water. And again, like on the last problem, make sure that you put this part in parentheses. Make sure that you have them both that way. You want them both in the denominator. Anyway, if you've done it right, it comes out to be 19.9%. So this solution is 19.9% ethylene glycol. And you probably imagined percent water would be 100% minus the ethylene glycol because there's only two pieces to it. Percent water, 80.1%. The concentration units handout will have more information on this, and I do encourage you to check it out. There's also some useful guides to help you with these kind of problems in the companion. So here's a problem you might see. Let's say you dissolve 92.0 grams of ethanol in 270 grams of water, and it says what's the mass percent ethanol in the solution? Okay, so mass percent, aka weight percent, grams of what you're looking at, which is ethanol, divided by total mass. So in this kind of problem, you'd have 92.0 on the top. You would divide by 92.0 plus 270, so mix them both together, multiplied by 100%. If you do that, it comes out to be 25.4% ethanol. So this solution, 25.4%, good to go. If you have molality, you can turn it into mole fraction, and mole fraction you can turn into weight percent, and weight percent you can turn into molality. All three of those are pretty interchangeable. But remember, in the big world of chemistry, molarity is still the important part. All right, molarity is the one that dominates all solutions big time. So we would be remiss in this kind of discussion if we didn't talk about ways to go from molality, mole fraction, and or weight percent to molarity and back and forth. And you can absolutely do this, but you have to remember that molarity is moles of solute per liter of solution. Liter is a volume, and all the other ones have grams, kilograms, moles. And if you want to go from mass and grams to volume, you need a density. So you're going to need the solution density to convert molarity to one of the other three new types of units. Same thing if you want to go from one of the other three types of units to molarity, you're going to need solution density. Now remember that solution density equals solute plus solvent, and all of these things will help us as we go through. So let's look at an example where we want to take a 10.7 molal aqueous sodium hydroxide solution. Let's stop right there for a second. Aqueous means the solvent is water. All right, aqueous is dissolved in water. And sodium hydroxide is going to be the solute. And the solution will be NaOH plus water. Okay, so back to your problem. Convert a 10.7 molal aqueous sodium hydroxide solution to mole fraction, weight percent, and molarity, big M, if the solution density is 1.33 grams per centimeter cubed. No problem. So what we're going to do in this problem is let's first convert the 10.7 molal number to mole fraction and weight percent, because honestly, those are a little bit easier to do. And once we have those down, then we'll go back and we'll turn that kind of information into molarity using the solution density. We won't need the solution density until we hit the molarity. The other ones here are pretty chill. When you're doing these kind of problems, there's always an assumption to start with. And if you're starting with molality, you want to assume you have 1 kilogram of solvent. And if you have a kilogram of solvent and the solution is 10.7 molal, that means you have 10.7 moles of solute. And remember, in this problem, the solvent is water and the solute is NaOH. If you have moles and grams of both solute and solvent, you can knock all of the first three right out. So let's figure that out. A kilogram of water is 1,000 grams. And if you take that 1,000 grams and divide by 18.02 grams per mole, you get 55.5 moles of water. So there we've got mass of water and moles of water. We have 10.7 moles of solute, NaOH. We can turn that into grams using the molar mass. So if you add up an Na, an O, and an H from the periodic table, it's about 40.0 grams per mole. That means 428 grams of solute, NaOH. So now you can see we have moles of solute, moles of NaOH. There it is. We have mass grams of solute. We have moles of solvent, which is this number right here. And we also have grams of water. Wow, this thing is not working very well for me, but you get the idea. All right. You've got all the pieces there. Now we can start putting them together into the first units. Mole fraction is moles of what you're looking at divided by total moles. So mole fraction sodium hydroxide, 10.7 moles NaOH divided by total moles, 10.7 moles of NaOH plus 55.5 moles of water, mole fraction 0.162. The mass percent or weight percent sodium hydroxide would be grams of NaOH divided by total grams times 100%. So there's 428 grams NaOH. We'll divide that by the 1,000 grams of water plus the 428 grams of NaOH, like total mass on the bottom, just NaOH on the top, times 100%. Mass percent, weight percent, 30.0% NaOH. So here we've got mole fraction and weight percent already. We didn't need to use the solution density at all so far. And notice how to solve these, we needed grams and moles of both solute and solvent. And that's how you can conquer those problems, no problem. We still need to conquer molarity. And remember, molarity is moles of solute over liters of solution. The good news here is that we actually already have moles of solute. The 10.7 moles of NaOH, which came from 1 kilogram total of solvent, the 10.7 is the moles of solute. That's the number we're going to use for molarity. But we also need liters of solution. So what people usually do is they take the grams of solute and solvent and add them together, and that's 1428. So in this solution, which is NaOH plus water, we have a total mass of 1428 grams, 1,428 grams. And this number now is what we can use with the density, the 1.33 number up here on the top. So if we take that 14.8 and you divide by the density, 1.33, you're going to get a number which is the centimeters cubed or milliliters. Remember, centimeter cubed and milliliter are the same. That's the volume of the solution. That's 1,070 milliliters. And if you convert that to liters, 1,000 milliliters per liter, that would be 1.07 liters. So I want to backtrack and highlight that a little bit. You want to add solute plus solvent grams, 1,000 plus 428 in this case. That gives you the total mass of the solution. So 1428, that's all the grams we have. That's the number you can use the density with. So 1428 grams divided by the density of the solution, 1.33. That's how we got the volume of solution. And 1.07 liters is what we want to use in molarity. So molarity, 10.7 moles divided by 1.07 liters of solution. Molarity, 10.0 molar. All right? That's kind of cool. Now, one little thing I can use to help you out here, molarity is almost always a smaller number than the corresponding molality. So in this problem, 10.7 molal was the molality of the solution, and we just calculated that the molarity, 10.0 molar. So molarity is smaller than molality, and most of the time, that's the case. Sometimes in really dilute solutions, they'll be about the same, but that's pretty rare for us. So just most of the time, molarity is a number smaller than molality, and that's a nice way to check yourself. Another unit, which is worth mentioning, although we won't do as much here, is called a parts per million. And a parts per million, ppm, is a very small concentration unit. And it's used a lot by environmental scientists, biologists use it sometimes, geologists, stuff like that. A part per million, 1 part per million, means, in all practical purposes, that you have 1 gram of a substance, the substance you're looking at, in a sample with a total mass of 1,000,000 grams. And 1,000,000, by the way, is 10 to the 6. So that's 1 gram in 1,000,000 grams. That's a pretty small amount. All right. Now, the density of water is about 1 gram per milliliter, like we've talked about. So if you have 1,000,000 grams, that's pretty close to 1,000,000 milliliters of water. So a lot of times people will make these kind of assumptions to make sense of what parts per million is actually about. There's nothing that says you have to have a parts per million, too. You can also have a parts per thousand, which would be 1 gram of substance in 1,000 grams of the bulk. You could also have a part per billion, which would be 1 gram of the substance in 1,000,000,000, or 10 to the 9th grams of substance. This parts per thousand is different than the parts per thousand we use in lab. In lab, we use parts per thousand as a measure of precision, how close your measurements are. And the smaller parts per thousand means that your measurements are greater. This parts per thousand is more like a molarity, or a molality for that matter. It represents how much of a type of a solute is in the whole solution or solvent. Kind of cool.